Welcome to the deep dive. We take your sources, we break them down, and basically give you the core insights fast.
Helping you get truly well-informed.
Today, we're tackling an experiment that, well, Richard Feynman famously said, has in it the heart of quantum mechanics.
And he also called it impossible to explain in any classical way.
That's a heck of a claim, right? And that's kind of our mission for this deep dive. We're plunging right into that impossibility.
Exactly. The double slit experiment. We want to unpack, what it tells us starting from the classical world we think we know, all the way to the, let's be honest, totally mind-bending quantum reality, and even the philosophical debates that are still going on.
So the goal is you walk away really understanding this fundamental puzzle, clearly.
That's the plan, a comprehensive picture.
Okay, let's do it. But before we get into the quantum weirdness, maybe we should set a baseline. Like, how should things behave, classically?
Good idea. Yeah, establish the normal before the weird. Classically, you've got two categories, particles and waves. Particles are kind of either. Like tennis balls, if you throw them at a wall with two slits.
Perfect example. Tennis balls. If only one slit's open, they land behind that slit. Simple.
Right. A single band.
Now, open both slits. What happens? Each tennis ball goes through either slit 1 or slit 2, not both.
So the pattern on the screen behind it is just the two single bands added together.
Exactly.
Yeah.
Just the sum. P12 equals P1 plus P2. Simple probability addition. No surprises.
Okay. Particles are straightforward. Either. But waves are different even classically, aren't they? The both-hand thing?
Ah, yes, waves. Think of water waves hitting those same two slits.
Okay.
A wave doesn't pick a slit. It spreads out and passes through both slits simultaneously.
And then things happen. Diffraction.
Right. As the wave squeezes through each narrow slit, it diffracts, it spreads out again. You can think of Huygens' principle here. Each slit becomes like a new source of little wavelets.
So you've got two sets of waves spreading out from the slits. What then?
They overlap. And this is where superposition and interference kick in. Superposition.
Yeah.
Meaning they just add up where they meet.
Essentially, yes. Where a crest from one wave meets a crest from the other, they add up constructive interference. Bigger wave, brighter spot.
And if a crest meets a trough?
They cancel out. Destructive interference. Basically, zero wave, dark spot.
So all this adding and canceling, what does the final pattern look like? It's not just two bands, is it?
Not at all. You get this very distinctive interference pattern, alternating bright and dark fringes, or bands.
Bright, dark.
Precisely. The central band is always bright because the paths from both slits are equal. But as you move out, the path difference changes, leading to alternating constructive and destructive interference.
And mathematically, this is different from the particles. You mentioned an interference term.
Critically different. With waves, the intensity is related to the square of the summed amplitudes. That calculation naturally produces this extra interference term, which can be positive or negative, creating the bright and dark bands. It's just not there for classical particles where you just add probabilities.
Okay, classical waves interfere. And this wasn't just theory for light. Someone actually showed this. Thomas Young.
Indeed. Back in the early 1800s, everyone thought light was particles, thanks to Newton. But Thomas Young did this brilliant experiment around 1801.
He used actual slits.
Initially, he used a thin card to split a beam of sunlight, essentially creating two coherent sources. Later versions used slits.
And he saw
colored fringes. The interference pattern, clear as day, direct evidence that light behaved like a wave.
Wow, that must have been a shock.
It was. He even calculated the wavelengths of different colors, but, Newton's authority was huge, so it took a while, and work by Fresnel, for the wave theory to really take hold. But for about a century, that seemed settled. Light is a wave.
Until the 20th century, quantum mechanics arrives.
Right. Things like the photoelectric effect suggested light also behaved like discrete packets. Photons.
So back to the double slit experiment they went.
Exactly. But with a crucial twist. They needed to see what happened with one particle at a time.
One at a time.
By turning the source intensity way, way down, so low that, on average, only one photon, or later one electron, was actually in the apparatus at any given moment. G.I. Taylor did early work with dim light in 1909.
And then with electrons. Things we definitely thought were particles.
Yes. Claus Janssen in 1961, that was a landmark. Then Pier Giorgio Merli and his team in Italy in 1974 got definitive single electron results. Stefano Farboni's team even filmed it building up dot by dot in 2012.
Okay, so light electrons. Has it stopped there? Or did they try bigger things?
Oh, it gets much wilder. This isn't just about tiny things. They've done it with neutrons, atoms,
Atoms, okay.
and even huge molecules. Get this.
Ugh.
Molecules made of over 800 atoms with a mass over 10,000 atomic mass units.
Wait, really? Molecules that big showing interference?
Absolutely. Which tells you this isn't some quirk of light. It seems to be a fundamental rule of nature, applying even to things we'd consider pretty solid objects. It scales up.
Which brings us right to Feynman's central mystery, the pattern that builds up. It's just impossible, classically speaking. How does it actually look?
It's profoundly weird. It happens in two stages. First, detection. Each thing, photon, electron, big molecule, always arrives at the screen at a single point. A flash. A dot.
Particle-like, localized. It hits here, not spread out.
Exactly. And where they land initially looks completely random. So far, so good for the particle picture, maybe.
But there's always a but in quantum mechanics.
There is. Over time, as more and more of these single particle-like dots accumulate,
Don't tell me.
they build up the wave interference pattern, the alternating bright and dark fringes.
No way. Each one lands like a particle, but collectively they map out a wave pattern.
Precisely the paradox. How does an individual particle, traveling alone, seemingly know about both slits to end up in the right place to form an interference pattern? It's like it interferes with itself. Classical physics just throws its hands up.
So what are they? Particles? Waves, this
Right.
wave-particle duality thing.
That's the term, yes. But it's maybe better to think they are neither classical particles nor classical waves. They're quantum entities.
Quantum entities.
And they exhibit properties we associate with particles or properties we associate with waves, depending on the experiment we set up to measure them. It's not like they flip a switch. The underlying reality is quantum, and our classical questions force a certain type of answer.
And Niels Bohr had a concept for this. Complementarity.
Exactly. Bohr's principle of complementarity. He said the wave-like and particle-like descriptions are complementary aspects of reality. Meaning you can see one aspect or the other, but never both in the same experiment. If you design an experiment to find out which slit the particle went through, particle aspect,
You lose the interference pattern, wave aspect.
precisely. And if you set things up to see the interference pattern, you fundamentally cannot know which slit it went through. They are mutually exclusive views.
Okay, that leads to the obvious question. If it lands as a particle, it must have gone through one slit or the other. What if we try to look? Put a detector at the slits.
The which way experiment? A perfectly natural question to ask. So physicists tried it. Put some kind of detector at each slit, maybe something that scatters a tiny bit of light off the particle as it passes. Just enough to tell us, aha, it went through slit 1 or slit 2.
Yeah, what happens to the pattern on the screen?
The result is, well, startling, as you said. The moment you gain that which way information, poof, the interference pattern completely vanishes.
Gone. Just like that.
Completely gone. Instead, what do you see? Two distinct bands on the screen, exactly like the tennis balls we started with.
Just some classical particles, wow.
This is often described as the collapse of the wave function. The act of measurement forces the particle out of its superposition of paths into a single definite path, slit 1 or slit 2.
And that measurement interaction destroys the delicate phase relationship needed for the waves to interfere.
That's the key. To look is to change the system.
Now, this observer effect,
Yeah.
it gets misinterpreted a lot, right?
Mm-hmm.
People think it needs a conscious person looking.
Huge misconception. It has nothing to do with consciousness. The observer is just any measuring device, any physical interaction that records which way information, an atom, a photon detector, anything.
So the physical interaction itself.
Yes. Any measurement strong enough to tell you the path involves a physical interaction, bouncing a photon, whatever. That interaction inevitably kicks the particle, transfers some momentum or energy.
Ah, so it disturbs it.
It disturbs its state, specifically its phase, in an unpredictable way. And that randomization of the phase relationship between the paths is what scrambles the interference.
And there's a more modern take involving decoherence.
Right. Decoherence offers a more detailed picture. It says that during measurement, the particle's quantum state doesn't just collapse, it becomes entangled with the detector.
Entangled, linked.
Linked in a quantum way. And then the detector, being a larger object, rapidly interacts and becomes entangled with its surrounding environment, air molecules, photons, everything. So the information spreads out. Exactly. The phase information, the waviness needed for interference, leaks out and gets distributed across this vast environment. It's not destroyed, but it becomes practically impossible to retrieve or see in the particle alone. The interference gets washed out into the correlations with the environment.
Okay, so the weirdness holds up. But There's math behind this, right? It's
Yeah.
not just hand-wavy analogies. How does the theory actually describe it?
Absolutely. The math is precise, even if the concepts feel slippery. The core mathematical object is the wave function, usually written as psi, the Greek letter.
And that contains everything we can know.
Everything knowable about the quantum system, yes. It's a complex mathematical function that basically assigns an amplitude and a phase to every possible state or position of the particle. It describes the probability wave.
And superposition is key here mathematically, too.
Crucial. The principle of superposition is built into the math. If the particle could go through slit 1, described by wave function 1, and it could go through slit 2, 2, then before we measure, its state is the sum. At total, it follows a 1 plus a 2.
The math literally says it's doing both.
In a way, yes. It embodies that potentiality. And this isn't just math on a blackboard. This ability to be in multiple states at once is what powers things like quantum computers.
But we don't see Ed directly. How does it connect to where the particle actually lands? A probability.
That's the Born rule, named after Max Born. It's the recipe for getting probabilities from the wave function. You take the wave function at a particular point, find its magnitude size, and square it. Px at q psi x, square the magnitude. That value gives you the probability density of finding the particle at that point x. Where the wave function magnitude is large, the probability is high. Where it's small, the probability is low.
And when you apply this rule to the superposition state, E1 plus Ed2.
That's where the magic happens mathematically. When you calculate E1 plus E2, you don't just get E1 plus E2, which would be the classical sum P1 plus P2. You get an extra term, the interference term.
The term we talked about earlier.
The very one. It depends on the phase relationship between E1 and E2. Where they're in phase, it adds, giving a higher probability, bright fringe. Where they're out of phase, it subtracts, giving a lower, even zero probability, dark fringe.
And if you measure which way?
The measurement interaction randomizes the relative phase. Mathematically, this makes the interference term average out to 0 over many particles. So E1 plus E2 reduces to just E1 plus E2 over, which is the classical P12, P equals P1 plus P2. The math perfectly captures the vanishing interference.
Incredible how the math mirrors the experiment. Then there's Feynman's approach. The path integrals. That sounds wild.
It's a completely different but equivalent way to formulate quantum mechanics. And yeah, it's conceptually mind-bending, Feynman said. Forget the wave function evolving. Instead, assume the particle takes every possible path from the source to a point on the screen.
Every path, like looping around the moon first.
Literally every path, no matter how crazy. An infinite number of them.
Okay. How does that give you an answer?
Each path is assigned a complex number, a phase, based on something called its classical action. To find the probability of landing at a point, you sum up the contributions, these complex numbers, from all the infinite paths leading to that point.
Summing infinity.
Mathematically, yes. And the interference pattern emerges naturally. Paths that are similar, like the ones going roughly straight through the slits, have similar actions and phases, so they add up constructively.
And the crazy paths.
The wildly different paths tend to have rapidly varying phases, so their contributions mostly cancel each other out. If you close one slit, you remove a whole set of paths from the sum, changing the result. It beautifully explains interference.
So we have this incredibly successful mathematical description, but it doesn't really tell us what's real, does it? Which leads to the interpretations.
Exactly. The math works, it predicts. But what does it mean? That's where interpretations diverge. They all agree on the experimental result, but offer vastly different pictures of the underlying reality. The double slit is exhibit A for all of them.
Let's touch on the big ones. Copenhagen, Bohr, and Heisenberg.
The traditional view for a long time, Copenhagen is quite pragmatic, almost anti-realist in some ways. They'd say the wave function isn't reality itself.
Not real. Then what is it?
It's epistemic. It represents our knowledge or information about the system, allowing us to calculate probabilities. Physics, Bohr said, is about what we can say about nature, not how nature is independent of us.
Oh, in the double slit for Copenhagen.
The electron's wave function is a superposition A1 plus 2. When it hits the screen, a measurement by a classical device, this wave function undergoes a real, instantaneous, and fundamentally random collapse.
Poof.
Poof. The superposition disappears, one outcome becomes actual. If you detect at the slit, the collapse happens there. Definite path, no interference.
But the sticking point is that measurement, right? What counts?
That's the measurement problem, Copenhagen's main challenge. It draws a line, the Heisenberg cut, between the quantum system and the classical observer apparatus, but doesn't precisely define where that line is or what triggers the collapse. It feels a bit arbitrary. Einstein famously hated the randomness aspect. God does not play dice.
Okay, then moving to something totally different. Many worlds. Everett.
Hugh Everett's idea from the 50s, radical. Many worlds says the wave function is real ontological. It's the complete description of reality. And crucially,
It never collapses?
never collapses. The entire universe, including observers, is described by one giant deterministically evolving wave function.
But wait, if it doesn't collapse, why do I only see the particle hit one spot? Or go through one slit if I look?
Because, according to many worlds, every time a quantum event with multiple possibilities occurs, the entire universe branches.
Branches, like splits.
Splits into parallel universes, one for each possible outcome. When the electron passes the slits, the universe branches. In one branch, it goes through slit 1, in another, slit 2.
And I split it.
You, the detector, everything splits. The U in the slit 1 branch sees it go through slit 1. The U in the slit 2 branch sees it go through slit 2. From within your branch, the outcome seems random, but the overall universal wave function contains all branches evolving deterministically.
Okay, my head hurts. Interference.
Interference arises from the structure of this universal wave function across the different branches.
Wow. Solves the measurement problem, I guess, but the price seems steep. Parallel universes.
That's the main criticism. It's ontologically extravagant, violates Occam's razor for many. Plus, these other worlds are, by definition, unobservable, making the theory hard to test directly, though some argue it's the simplest interpretation mathematically.
All right, one more major one. Pilot wave theory. De Broglie-Bohm.
Yes, an older idea revived by David Bohm. This one tries to restore determinism and a more classical notion of reality. It says reality has two parts.
Cool.
There's a real particle with a definite position at all times, just like a classical particle, and there's a real physical pilot wave that guides it.
A guiding wave. Okay.
The particle's motion is completely deterministic, governed by this pilot wave. What looks like randomness is just our ignorance of the particle's exact starting position within the wave.
So in the double slit, how does that work? Does the particle go through one slit?
Yes. The particle itself goes through only one slit, but the pilot wave goes through both.
Uh-huh.
The pilot wave passes through both slits, interferes with itself, and creates a complex landscape called the quantum potential. This potential then pushes and pulls the particle, guiding it deterministically into the regions of constructive interference and away from destructive interference. That's how the pattern builds up.
And if you put a detector there?
Placing a detector changes the pilot wave itself, alters the quantum potential. The new potential no longer guides the particles into an interference pattern, but into two separate bands. No wave function collapse needed.
Interesting. Does it have downsides?
It restores determinism and particle trajectories, which some like. But the pilot wave and quantum potential have to be explicitly non-local. They can instantaneously influence things far away. That spooky action at a distance bothers some people, though experiments confirm non-locality is real.
What a journey. From Young's simple observation over 200 years ago
to this fundamental paradox that still challenges our deepest intuitions about reality. Is it a particle? Is it a wave? Does looking change it? What does the math mean?
It really is, like Feynman said, the heart of it all.
Yeah.
Wave-particle duality, the observer effect.
Mm-hmm.
These aren't going away, and no single interpretation satisfies everyone.
But here's the amazing thing. This weirdness isn't just a philosophical curiosity anymore. It's the bedrock of new technologies.
Right, we're actually using these bizarre quantum effects.
Quantum computing hinges on superposition, the particle exploring multiple paths at once, in a sense.
Quantum cryptography uses the observer effect, the fact that measuring disturbs the system to guarantee secure communication.
And quantum sensors exploit the incredible sensitivity of interference effects to measure things with unprecedented accuracy.
So the paradox is becoming progress. And the research continues, right? Pushing the limits.
Definitely. Trying interference with even bigger objects, testing the boundary between quantum and classical, exploring variations like slits in time. It's a very active field.
So wrapping this up, what's the final thought for you, the listener, grappling with this?
I think it's that the double slit experiment, in its elegant simplicity, forces us to confront the limits of our classical intuition. It's this inescapable window into the quantum realm, showing us that the fundamental nature of reality is far stranger and maybe far richer than we ever imagined. It's an invitation to keep questioning, keep exploring.